Hi everyone, nice to meet you in this way. I'm Guixuan from GTT Technologies. Today, I would like to talk about some applications of the FactSage, including the assessment of few slags, especially for the use in engine flow classifiers, and the model development for suspension viscosities. First, I will introduce what is an optimum slag system. Of course, it depends on different processes, different vectors, and different conditions. The next important issue I'm going to talk about is how to achieve this optimum slag system by experimental work or by theoretical calculation. Then I will move on to the next topic concerning the viscosity estimation for the suspension system. Even though the suspension viscosity cannot be directly calculated by using FactSage, but FactSage provides some important information, for example, phase distribution, the viscosity of the remaining liquid slag. This information is really necessary to further derive the viscosity of the suspension system. In the end, I will mention a little bit concerning the improvement in viscosity prediction for the suspension systems. Okay, let's look at what is an optimum slag system in engine flow classifiers. We know normally engine flow classification is a high temperature, high pressure process. Concerning the slag related issues, we need to consider two aspects. First, we need to make sure the slag need to be smoothly discharged from reactor. On the other hand, we need to minimize the refractory corrosion by molten slags. For this purpose, we need to consider these thermophysical and chemical properties, for example, viscosity, subtension, and so on and so forth. But today, I will focus on three significant parameters, including viscosity, liquid temperature, and reactivity with refractive material. For the viscosity, actually, there is a target viscosity range between 5 and 25 pascal second. That means if the viscosity is too large, the slag tapping blockage may occur, while when the viscosity is too small, this may result in more serious refractory corrosion. Anyway, with considering these parameters, how can we obtain the optimum slag system? By doing experimental work, viscosity measurements as well as the corrosion test, both are really time consuming. And second, also not possible to consider all possible compositions. So in the end, we may select limited amount of the samples. For example, here we select the light samples for this 5-component system, and after experimental work, we may find out the slag 3 is the best one, but please keep in mind the result obtained here is not a global optimum slag system because we only compare these light samples. So how about the others, the other candidates? So from this point of view, it's necessary to do some pre-calculations, for example, by using FactSage. Here we combine the viscosity data with the liquid temperatures. You see, in this figure, this three-dimensional surface corresponds to the viscosity, and these black curves are referring to the liquid temperatures. And then we can easily find our targeted viscosity range is somehow located here, indicated by this purple circle. You may notice this purple circle is located within this fully liquid zone because in the region below the liquid temperature, for example here, the viscosity could be sharply increased by the crystals due to crystallization. That's why I defined this region with a high risk. So we try to find our solution, our optimum slag system within this purple circle. The next issue coming to us is which slag is the best, slag A or slag B or slag C, because the viscosity of the slag A is somehow the same with that of slag C. Can we say these slags are the same? No, I don't think so, because we need to consider another aspect, refractory corrosion, as I mentioned before. Here, if the refractory is the alumina-based material, then we can add phase diagram to show such difference. For example, for this region, this is the two phases region, including the alumina and slag. That means at this temperature, this liquidous line indicates the maximum solubility of the alumina in molten slags. So, in other words, the slag A or slag B has a higher driving force to dissolve the alumina than slag C. So, we can say the optimum slag system is somehow the slag C or around slag C. To further determine the optimum slag system, we also need to consider the fluctuations, because I don't think so we can achieve the constant slag composition, constant operating temperature, and so on. So by analyze the influence of the fluctuations, for example, for the operating temperature, we can have more liquidous slide, especially at low temperature. Here we see 1350 degrees C, we can see this slag C already outside the free liquid zone. That means we have to suffer from the risk of the sudden increase in viscosity due to the crystallization. Okay, so we need to shift the slag C to the left-hand side, somewhere here. But how close to the liquidous line for the candidates of the optimum slag system, it really depends on the fluctuation information. So we need to do some experimental work to validate our optimum slag system, but only with limited amount of the experimental work. Okay, that's it for the first part. So we can turn to the second part concerning the viscosity of the suspension system, because this is also very common during the operation of the engine flow gasification. Okay, how to estimate the viscosity contribution from the crystalline phases? Here we use the Einstein-Losko equation to derive the relative viscosity, and then further multiply the viscosity of the remaining liquid slag, then we can get the suspension viscosity showed in this equation. And by doing this, of course, we need to use, for example, FactSage with the proper database to calculate the mass fraction of the crystals. Here we assume the mass fraction is equal to the volume fraction. That's fine for the first rough estimation. Okay, here's the result. This is the one-dimensional phase mapping, and this is the phase distribution. So we will see how the slag phase change with respect to temperature, and we will also get the composition of the remaining liquid slag, and based on this we can calculate the viscosity using the viscosity modeler in FactSage. And then we also can get this mass fraction of the total solid phases. Based on this information, according to the Einstein-Losko equation, we can get our first result. You see the suspension viscosity increases with increase in the mass fraction of the solid phases. Yeah, the variation trend of course depends on the formation of the crystal phases and different crystal phases and so on and so forth. Here we can see another interesting phenomenon. There is a viscosity maximum for the viscosity of the remaining liquid slag. This is possible because the composition will be changed during crystallization. Actually, also possible for the suspension viscosity can have the local viscosity maximum. This is also possible due to the combined effect of the composition change in the remaining liquid phase and also the physical effect from the crystalline phases. Actually, this phenomenon has been observed in Michel's group in Research Center Munich. Okay, next part I want to share with you is how to improve the prediction for suspension viscosity. Of course, we need to replace mass fraction by volume fraction as a first step. And then by doing this, we need to know the density data for the crystals, also for the molten slags. You see, for the zinc sample, we find the density data for these 4 crystal phases. Okay, here only for room temperature. So if we want to get the density at high temperature, we need to know also the thermal expansion coefficients. And for the molten slags, there are many existing density models. So you can pick up one of them. Of course, it depends on the slag system or slag composition you are working on because each density model has their own limitations. But anyway, we can combine these two information can get the volume fraction of each crystalline phases. In addition to the volume fraction, we also need to pay attention to other parameters, including the crystal size distribution, and crystal morphology, because all these parameters will influence the maximum packing fraction and further influence the effective volume fraction. This is really important. For example, if we look at this figure, at a constant volume fraction of the solids, with decreasing the particle size, the suspension viscosity will increase. So, because this is due to the different effective volume fraction. Another interesting phenomenon I want to share with you is the constant aspect ratio. For example, here, this is the olivine phases. The aspect ratio is 2, round about 2. Even the crystal will glow from temperature 1100 degrees C to 1200 degrees C. If this result is valid for also other crystal phases, then based on this, we can modify our Einstein-Roscoe equation in this way. That means we can derive the viscosity contribution from each crystalline phases. That means each crystalline phases have the different viscosity contribution, even have the same volume fraction. This is really interesting. But of course, to assess these model parameters, we need much more viscosity data together with the quantitative information, including the aspect ratio, crystal size, then to further improve the viscosity prediction for suspension system. Yeah, that's it. Thank you for your attention.